LM3405, constant current regulators for powering LEDs from National Semiconductor. Welcome to the training module on National Semiconductor's LM3405 constant current regulators for powering LEDs. The intent of this training module is to introduce the operations of the LM3405. Integrated with a 1 amp power switch, the LM3405 is a current mode control switching buck regulator designed to provide a simple, high-efficiency solution for driving high-power LEDs. With a 0.205 volt reference voltage feedback control to minimize power dissipation. Switching frequency is internally set to 1.6 MHz. Allowing small surface mount inductors and capacitors to be used. The LM3405 utilizes current mode control and internal compensation, offering ease of use and predictable high-performance regulation over a wide range of operating conditions. Additional features include a user-accessible Enable Dim pin for enabling and PWM dimming of LEDs, thermal shutdown, cycle-by-cycle current limit, and overcurrent protection. The LM3405 is a PWM current mode control switching buck regulator designed to provide a simple, high-efficiency solution for driving LEDs with a preset switching frequency of 1.6 MHz. This high frequency allows the LM3405 to operate with small surface mount capacitors and inductors, resulting in LED drivers that need only a minimum amount of board space. The LM3405 is internally compensated, simple to use, and requires few external components. The LM3405 supplies a regulated output current by switching the internal NMOS power switch at constant frequency and variable duty cycle. Capacitors C3 and diode D2 in the figure are used to generate a voltage VBoost. The voltage across C3, VBoost minus VSW, is the gate drive voltage to the internal NMOS power switch. A switching cycle begins at the falling edge of the reset pulse generated by the internal oscillator. When this pulse goes low, the output control logic turns on the internal NMOS power switch. During this on time, the SW pin voltage, VSW, swings up to approximately Vn, and the inductor current, IL, increases with linear slope. IL is measured by the current sense amplifier, which generates an output proportional to the switch current. The sense signal is summed with the regulator's corrective ramp and compared to the internal amplifier's output, which is proportional to the difference between the feedback voltage and Vref. When the PWM comparator output goes high, the internal power switch turns off until the next switching cycle begins. During the switch off time, inductor current discharges through catch diode D1, which forces the switch pin to swing below ground by the forward voltage VD1 of the catch diode. The regulator loop adjusts the duty cycle D to maintain a constant output current IF through the LED by forcing FB pin voltage to be equal to Vref, or 0.205 volts. To properly drive the internal NMOS switch during its on time, VBoost needs to be at least 2.5 volts greater than VSW. Large value of VBoost minus VSW is recommended to achieve better efficiency by minimizing both the internal switch on resistance, RDS on, and the switch rise and fall times. However, VBoost minus VSW should not exceed the maximum operating limit of 5.5 volts. When the LM3405 starts up, internal circuitry from VN supplies a 20 milliamp current to the boost pin, following out of the boost pin into C3. This current charges C3 to a voltage sufficient to turn on the switch. The boost pin will continue to source current to C3 until the voltage at the feedback pin is greater than 123 millivolts. There are 4 methods to derive VBoost. The first method is shown in the internal block diagram. Capacitor C3 is charged via diode D2 by Vn. The second method for deriving the boost voltage is to connect D2 to the output as shown in Figure 1. The gate drive voltage in this configuration is VBoost minus VSW equals Vout minus VD2 plus VD1. Since the gate drive voltage needs to be in the range of 2.5 volts to 5.2 volts, the output voltage Vout should be limited to a certain range. The third method, shown in Figure 2, can be used in applications where both Vn and Vout are greater than 5.5 volts. In these cases, C3 cannot be charged directly from these voltages. Instead, C3 can be charged from Vn or Vout minus a Zener diode voltage by placing the Zener diode D3 in series with D2 as shown. When using a series Zener diode from the input, the gate drive voltage is Vn minus VD3 minus VD2 plus VD1. The fourth method, shown in Figure 3, can be used in an application which has an external low-voltage rail, VEXT. C3 can be charged through D2 from VEXT, independent of Vn and Vout voltage levels. Again, for best performance, ensure that the gate drive voltage, Vx minus VD2 plus VD1, falls in the range of 2.5 volts to 5.5 volts. Here shows a typical application using the LM3405 regulator driving a single LED. The boost voltage can be derived from Vn or Vout. The boost to SW voltage, VBoost minus VSW, should never exceed the operating limit of 5.5 volts and must be greater than 2.5 volts for optimum efficiency. In this circuit, the maximum Vn is 5 volts, and therefore the boost voltage is derived from Vn. The LM3405 driver tightly regulates the VB pin voltage to 205 millivolts typically, and this allows the LED current, IF, to be set by the listed equation. In case of an overcurrent, the internal current limit will trigger and turn off the internal power switch on a cycle-by-cycle basis. In case of an overvoltage, sensed at the VB pin, the internal power switch is turned off. The LEDs can be dimmed by applying a PWM logic signal to the EN dim pin of the LM3405 driver as shown in the figure. A logic high at VPWM enables the IC, and a logic low disables the IC. In this manner, the LED current is turned on and off. In order to eliminate flicker, the lowest PWM dimming frequency is normally chosen to be above 100 Hz. The upper end of the PWM frequency is determined by the turn-on delay of the LM3405. The average LED current is controlled by T-on, T-PER, or both, and is perceived by the eye as a brightness change. The LM3405 LED driver can be used to drive multiple LED strings in parallel as shown in the figure. The current in the primary branch with LED 1 and LED 2 will be tightly regulated by the feedback loop. The current in the secondary branch with LED 3 will be regulated based on Vout, forward voltage of LED 2 and LED 3, I should say, and R2. The value of R2 can be adjusted to get the desired brightness for LED 3. Multiple LEDs can be paralleled and connected between Vout and VB as shown in the figure. The voltage at the VB pin is regulated to 205 millivolts by the control loop, and therefore the current in R1 is fixed. Vout is determined by the LED with the highest forward voltage. This solution has the advantage of having a single resistor set the total currents in the LEDs, but has no control of equal current sharing between the LEDs. The inductor value determines the output ripple current. Lower inductor values decrease the size of the inductor but increases the output ripple current. An increase in the inductor value will decrease the output ripple current. The ratio of ripple current to LED current is optimized when it is set between 0.3 and 0.4 at 1 amp LED current. The table lists the recommended inductance range. An input capacitor is necessary to ensure that Vin does not drop excessively during switching transients. The primary specifications of the input capacitor are capacitance, voltage rating, RMS current rating, and equivalent series inductance, ESL. A 10 microfarad multi-layer ceramic capacitor, MLCC, is a good choice for most applications. The output capacitor is selected based upon the desired reduction in LED ripple current. A 1 microfarad ceramic capacitor results in a very low LED current ripple for most applications. Due to the high switching frequency, the 1 microfarad capacitor alone, without feed-forward capacitor C4, can filter more than 90% of the inductor ripple current for most applications where the sum of LED dynamic resistance and R1 is larger than 1 ohm. The feed-forward capacitor C4, connected in parallel with the LED string, is required to provide multiple benefits to the LED driver design. For most applications, a 1 microfarad ceramic capacitor is sufficient. In fact, the combination of a 1 microfarad feed-forward capacitor with a 1 microfarad output capacitor leads to less than 1% ripple current flowing through the LED. The catch diode D1 conducts during the switch off time. A Schottky diode is required for fast switching time and low forward voltage drop. The reverse breakdown rating of the diode must be at least the maximum input voltage plus appropriate margin. To improve efficiency, choose a Schottky diode with a low forward voltage drop. A standard diode such as the 1N4148 type is recommended. For VBoost circuits derived from voltages less than 3.3 volts, a small signal Schottky diode is recommended for better efficiency. A good choice is the BAT54 small signal diode.